Bismillahirrahmanirrahim. Today's video will be discussing end chapter question 14.44 from Fundamentals of Electric Circuit by Mr. Alexander and Sadiku. And this is on the request of a student. The question relates to series parallel circuit at resonance. So let's see the question. This is the circuit. We have to find the resonant frequency omega naught. And also we have to find the input impedance Z at the resonant frequency. So this is the circuit. You can see these two are in parallel, but these two are in series, and when added they'll also become parallel to this. So this is called series parallel circuit. Now normally the first part, first of all, we'll find out. And what we have done is that I have brought it here. So they are now in one branch. Looks like this same in parallel with this. Then an important point that for series circuit or parallel resonant circuit, the resonant frequency was given by omega naught is 1 over under root LC. But for series parallel circuit, we can't use this formula. So we have to derive the formula from this circuit. So let's see how to proceed. The first thing we'll do is convert the circuit into phasor form. So we know L will become j omega L. Now since we don't know the value of omega, so we'll just write j omega and the value of L. And similarly, capacitor is 1 over j omega C. And now these two adding, this will become the total value. And we have to keep in mind that the resonance results from when the imaginary part of the transfer function is 0. So that is what we'll try to achieve to find omega naught. And we'll understand for this one as we go on. What I have done, we could have solved this as Z in, but that will be more difficult because this multiplied by this and parallel this. So solving that will be difficult. So it is better to solve these as admittance or Y. So we'll write Y. Y is 1 over 1 here, 1 over j omega L, and 1 over this whole part. And from here, this goes up 1000 divided by 20, so it will be 5 at the top, j omega. This one we take LCM, and further we'll just invert this. This goes up. And now we need to eliminate the complex terms in the denominator. So to eliminate this, we have to multiply by the same function, same terms, except by the changing the sign. So here it was 1 plus j omega, we'll now write 1 minus j omega, and to balance, we'll also write the same thing at the top. Now look here, when we multiply, it will be 1 square a minus a plus b, and a minus b. Formula is a square minus b square. So 1 square and minus b. This is b square. Now j square will be minus 1. And we have minus between these two. So it will be plus. Plus omega square. And then this term into a square. So we were here. Now we need, now this is the real value, no more j in this, but we have to separate these two terms to separate the imaginary or j omega terms. So we broke down this into two parts, the real part and the imaginary part. And now we will collect Okay, what I have done here, I have just first of all added an extra step, is that is j multiplied by j will be j square, which will be -1, minus and minus plus, then is the omega square, and then this multiplied by this will be 8.1 10 raised to the power -12, -6, -6, -12, and similarly the denominator when we open the square here. And now we will collect the imaginary terms, this one and this one, to one side. So we've collected the imaginary terms here and the real terms here. And now, as the conditions, we have learned that at the resonance, the imaginary term has to be 0. That resonance imaginary of y has to be 0. That means this term has to be equal to 0. So this is equal to 0. From here, we'll find omega naught. So cross multiply and just collecting the like terms, omega terms on one side and the whole number on the other side. And now taking common from here, omega square common. Now if you solve this, now look carefully, this is 9 10 raised to the power -6. And from there we have to subtract 40.5 into 10 raised to the power -12. So this is very, very small, negligibly small. And therefore we'll just write 9 into 10 raised to the power -6 omega square. You can use your calculator to see that you will get this result. And from here, omega square is now this term denominator, and solving, omega will be 2357 radians per second. We can write this in kiloradians as well, 2.357 kiloradians. So this is the first part. Now we have to find Zin. Now we have almost found Yin, so we'll just use that to find Zin. This was our Yin. We had already seen that this part has to be 0 at the resonance. So this is gone. So Yin is the part remaining here. And now that we have found out the value of omega, we'll put that value 2357 square, and solving, we get the answer 1.00049999. So Yin we have found. Now Zin will be just inverse of it. So Zin is 1 over Yin, is 1 over this value, which is again approximately equal to 1 ohm. So this is the answer. I hope you have been able to follow this. Please let me know through your comments. Thank you.